This problem asks us to use the differential rate law for an equation which has two reactants. We have hypochlorite ion and hydroxide ion. So we know right off the bat that the general format of the rate law would be something like as follows. And our task is to use the information in the problem to find not only the values of x and y, the exponents, but they also want us to find the value of the rate constant. And then down at the bottom, they even give us some initial concentrations to plug in once we've got the rate constant and solve for the rate itself. So let's turn to the data table. They only give us 3 experiments to look at. And thankfully, the 3 experiments they gave us enable us to eyeball the problem, because in comparing lines 1 and 2, the hydroxide concentration stays the same. Well, if the hydroxide concentration stays the same and the ClO2 concentration doubles, and in response to the doubling of the concentration of ClO2, we note that the rate changes by a factor of, please note carefully that there's a difference in the exponents. The 5.75 is times 10 to the negative second, and the 2.3 is to the negative first. That's a times 4 difference. The only way that you get a times 4 difference when you double the concentration is when the value of the exponent is 2. Now let's look at the next 2 lines in the table. Lines 2 and 3, the ClO2 concentration stays the same. The hydroxide concentration is half as much. And what happens to the rate? Well, this time the exponents are the same, 2.3 times 10 to the negative second and 2.1 times 10 to the negative second. That is a times half. So here we have the rate multiplier being the same as the multiplier for the reactant hydroxide ion. And the only time we experience that is when the exponent is 1. So if we know now something about the differential rate law, at least we know the exponents, we can say, alright, rate equals K times the ClO2 concentration squared times the hydroxide concentration to the first power. We can answer part A. Next, they ask us to find the value of the rate constant. Well, to do that, we can pick any of the experiments and plug in the numbers that they give us and solve. I'll just use the first experiment that they give us, and they say the rate in the first experiment of 5.75 times 10 to the second should be equal to some rate constant K. And then I'm going to plug in the value of the ClO2 concentration, 0.0500, and I'll raise it to the exponent that we know. At this point it's to the second power. And then we'll multiply that by the hydroxide concentration in that first experiment to the first power, and then we'll solve. We're solving for K. After pulling out your calculator, this one works out to be 230. And that should work out the same no matter which of the 3 experiments that you choose to plug in for. Now for part B of the problem. They're going to give us an initial concentration of ClO2 and an initial concentration of OH-. And they're saying what's the initial rate? Well, now that we know that the value of K is 230, we can write a more complete rate law. The rate will always be the value of the rate constant K, 230, times ClO2 concentration times hydroxide concentration, is the ClO2 concentration is squared, times hydroxide concentration to the first power. Well, we're just going to plug in the numbers that they give us. So that would be 0.165 squared, and we'll multiply that by 0.0844. Plug that into your calculator, and we arrive at 0.528. And rates are stated as moles per liter per second. And so we just write that down.